In Module 3, we discussed in detail expectation and variance, starting with discrete random variables, going on to continuous random variables, and then extending the definition to functions of random variables in single variable, then on to multiple random variables, functions of multiple random variables. We worked out example problems, and then we discussed some concepts relating to expectation and variance, such as the statistical distribution of sample mean and sample variance, and the formula for estimate of population variance given sample variance. We are going to switch to a new module and new set of topics, if you will. And the first topic that we're going to discuss is normal distribution. This will be module 4. In module 4, will be entirely on normal distribution. Then we will go on to application of normal distribution in module 5, which is a load strength interference or probabilistic design. And that's an engineering design application of normal distribution. And then we will go on to discuss other probability distributions in module 6 and so on. Okay, so let's get started with normal distribution. So far, we've discussed this PDF without any specific concrete mathematical form. The property that we derived, all the formulae we've derived, has not assumed any specific mathematical form of PDF. All we have said is the PDF has to integrate to 1 between minus infinity and plus infinity. And beyond that, we have not specified the mathematical form of the PDF. And every formula that we have derived so far in terms of that used PDF is valid regardless of the nature of the distribution. Now we will concretize this PDF with a specific form, and that's the form of the normal distribution. And it's a very common distribution, and the PDF has this mathematical form. And if you notice here, this PDF is defined in terms of two parameters, mu and sigma. If you change mu and sigma, the shape of the curve that you get, the PDF curve that you get, will change, and therefore normal distribution is a two-parameter distribution. Depends on mu and sigma. Mu is the mean value, and sigma is the standard deviation of a normal distribution. And here is one normal distribution with a mean value of 0 and a standard deviation of 20, and the same normal distribution with a mean value of 0 but a standard deviation of 40. And you can see that the distribution with larger standard deviation is more dispersed. Now, we rarely manipulate this mathematical form by hand. We either rely on computer or tables, as we will see shortly. So this is the probability density function of the normal distribution. And recall that we have we estimate the probability by integrating the PDF between limits of a and b, which gave us the probability that x would lie between a and b. What if the lower limit were to be minus infinity? So the probability that the random variable would be less than a specific value x is minus infinity to x integral of the PDF. So previously we had the probability that x would lie between a and b as being integral going from a to b of PDF. Now, instead of that, let's say we want the probability that the random variable would be less than a specific value x. Then the lower limit becomes minus infinity. And then what you get is what is called the cumulative distribution function. In the reliability context, the cumulative distribution function really represents the fraction of the total population that has failed at any specific instant. So if x were to be time, as we would going forward, we will later define x, the the random variable to be time in our case in a reliability context, then this f of t would represent the fraction of the total population that you put on test that have failed at a specific time t. So think of always the cumulative distribution function as the fraction of the total that has failed. And the CDF, or the cumulative distribution function, has the form that you see here, and it always starts with 0, because at start of the test, 0 of the population have failed. And at the end of the test, all the samples have failed. Therefore, it will always end with 1. And how it rises depends on the specific mathematical form of the PDF that we've assumed. So the CDF, the cumulative distribution function, for a normal distribution is as shown here. Again, it depends on these two parameters, mu and sigma. Now, the disadvantage of having a CDF like this is it depends on mu and sigma, and different situations will have different mu and sigma, so it's very hard to standardize this CDF. Instead, it is more, if there is a way to standardize this CDF by changing the variables, then we can create a table, a computer generated table, which will be valid regardless of mu and sigma. So that's what we are going to do. So to standardize application of normal distribution to different problems with different means and standard deviation, what we're going to do is a variable transformation. We're going to define this variable z as shown here, x minus mu over sigma is z. And that in turn allows us to express the PDF this way and the CDF this way. I need to explain something about the PDF here. You notice here there's no longer a sigma that we had before. Here, the sigma is gone. This now turns out to be our newly defined variable z. So we no longer have a sigma. So in other words, sigma is equal to 1. Why is that the case? We'll see that in a second here. And then you can see here the exponent becomes z squared over 2. Okay, that part is clear, but why sigma becomes 1 is not clear. So let me go through and show you what the standard normal variable transformation does. Z is x minus mu over sigma. So if I were to ask what is the expected value of z, what is the mean value of z, that is nothing but expected value of x minus mu over sigma, which is 1 over sigma, because sigma is a constant, expected value of x minus mu, which I can write as 1 over sigma, expected value of x minus expected value of mu, because expectation of sum is sum of expectations. And this I can write as 1 over sigma. Expected value of x is mu. Expected value of a constant is also mu. So this is equal to 0. So the expected value of z is 0. How about the variance of z, which is variance of x minus mu over sigma? And I can take out the sigma, so that's 1 over sigma squared. Remember the formula that variance of a constant times a quantity is constant squared times variance of the quantity, x minus mu. And now I can apply the other formula that I know, which is variance of quantity plus a constant is just equal to the variance of the quantity. So this is equal to variance of x, which is equal to sigma squared. So that's sigma squared over sigma squared, and that's equal to 1. So in other words, the standard deviation is 1, mean is 0 for the standard normal variable. So that's the reason why that sigma term went away in the PDF of standard normal distribution. So now this expression for CDF is difficult to integrate by hand, so we use computer integrated, and we can get a table for different values of z. I can estimate my CDF, which is denoted by phi of z. So this quantity is the phi of z here, which is the CDF. So we will use notation phi of z specifically when it comes to normal distribution. More generally, we will use the notation cap f for CDF, but specifically for standard normal distribution, we will use the notation phi. So this is phi of z for various values of z. And as you notice here, there are no negative values of z. There are only, typically, you only write the table in terms of positive values of z. So the way this table is to be read is, this is z value of 0, and this is 0.01, etc. This is the 100th place, the value change with 100th place. This is 0.02. So for z value of 0.02, this is the CDF. 0.03, this is the CDF, and so on. So for point, say 45, that would be my CDF corresponding to a z value of 0.45. What if I had negative values of z? Because it's possible for me to have negative values of z when you have x value less than mu. Then you'll have negative value of z. What if I had negative value of z? Then we know this property of a normal distribution, because normal distribution is symmetric. Phi of negative z is 1 minus phi of z. I need to explain this pictorially. So let me explain that. Since the normal distribution is symmetric, this corresponds to z equal to 0. So since the normal distribution is symmetric, if I have a negative value, this region here is the same as this region here. And so phi of negative z, this is equal to 1 minus this phi of, so let's call this z n for negative value, or okay, phi of zn, and let's call this z positive. So this is 1 minus phi of z positive. So, and remember, zn is negative of z positive. So, and that follows from the nature of the normal distribution, the symmetric nature of the normal distribution, that allows us to create a table only for positive values of z. And if you have negative values of z, you would use this formula here. And this is from Wikipedia. This table seemed clean, therefore I used this here as a reference for you. And we will use this table to work through example problems. So the value goes up to around 4. And the reason why you don't go much above is because, as you can see, as you get to larger and larger z values of around 4. And what you see is that there are lots of 9s. The probability is very, very, very close to 1. Okay. Now you can use this z to determine limits. Like, for instance, what if I wanted to know plus or minus 3 sigma limits? I know that z has a standard deviation of 1. Therefore, a 3 sigma would correspond to a z value of 3. And so now I can find out what is the probability that a part will lie between plus or minus 3 sigma limit. So now if you notice here, a value of z value, the CDF corresponding to a z value of 3 is 0.99865. And so what I would like to figure out is what is the plus or minus 3 sigma limit, okay, as an example. So let's say I have, okay, z equals 0 here, z equals 0 here, and this is plus 3, and this is minus 3. And we know that this expression here, this quantity here is f of CDF of minus 3. Minus 3 is the 1 minus the CDF of 3. And CDF corresponding to 3 we saw was 0.99865. And what we want to know is what is the area between these limits of plus or minus 3 sigma. So normally we have, with any manufacturing process, we have something that we would describe as process capability. And we would say, okay, what if I had a tolerance limit and the manufacturing process that gives me an ability to achieve the tolerance limit to within a plus or minus 3 sigma capability. So in other words, this is describing the manufacturing capability. And we will assume in this class, for purposes of concreteness, for sake of concreteness, we will assume that the manufacturing capabilities are 3 sigma on our limits. Okay. And it doesn't have to be 3 sigma. It could be 2 sigma, it could be 4 sigma, it could be 5 sigma, it could be whatever. But for purposes of concreteness, we will assume manufacturing capability given a dimensional tolerance to be plus or minus 3 sigma. So what does the plus or minus 3 sigma mean? What is the population that would lie within your tolerance limit? So this corresponds to an x value here. This is your lower limit. So I'm going to call it x sub L. And this corresponds to an upper limit. I'm going to call it x sub U. So what we are asking is, what is the population that will lie between your tolerance limits given manufacturing capability of plus or minus 3 sigma. Okay. Now we know, given the distribution, the probability that we seek, so x lying between n x u is equal to 1 minus 2 times phi of 3, because the lower limit is 1 minus phi of 3, the upper limit is phi of 3, so 1 minus 2 times phi of 3 is the limit that we seek. Oh, I'm sorry, this is not 2 times phi of 3, it's 2 times 1 minus phi of 3. Okay, so that is the population that population that will lie between the limits of plus and minus 3. This is equal to 2 times phi of 3 minus 1, and that's equal to 2 times 0.99865 minus 1. That's equal to 0.9973. So in other words, between the limits of plus or minus 3 sigma, the population that we would, the acceptable population would be 99.7%. So this is the 3 sigma limit, plus or minus 3 sigma production capability. That's the population that would lie between plus or minus 3 sigma. Finally, an important property of normal distribution is that if you have sums of, if you have, say, multiple random variables and they're all normally distributed, let's assume x1 is normally distributed, x2 is normally distributed, and sum of normal distribution is also normally distributed, simply because if you notice, using our expectation and variance formulae, so let's say y is x1 plus x2 and so on till xn. The expected value of y is, let's call this mu sub y, and that's equal to sum of mu I. We know because of our addition formula for expected quantities of independent quantities. Let's assume x1 and x2 are independent. Then expected value of y, the sum, is sum of the expected values of each of my individual normal distribution. Therefore, this also turns out to be a normally distributed, and that property is called the reproductive property of normal distribution. The variance, as we know, sigma y squared is summation of variance of the individual normal distributions. So this is called the reproductive property of normal distribution. And what if I have a large number of non-normally distributed quantities, possibly non-normally distributed, and as this n tends to infinity, the independent variables is normally distributed, and that is called the central limit theorem. So these are some important properties of normal distribution. One is the reproductive property, and the other is the central limit theorem. So with that, we will stop this module on normal distribution.